Yeah, all right. So thank you for the introduction and thank you. All right, thank you. Okay, so here's a plane. We all are very familiar with the notion of trilateration of the plane that says that if you have three non-collinear points, like these landmarks, any other point, for instance, the red point or the yellow point, is uniquely described by the distance to those landmarks. Well, the notion of resolvability is a generalization of the notion of trilateration, is a kind of multilateration of any metric space, not just the Euclidean space, okay? So in the abstract, we're gonna be given a metric space x comma d, and we're gonna say that a subset of points resolves that metric space if this transformation that to every point in the space as such as a distance to every point in the set R is 1-to-1. So one can think of R1 up to Rk as landmarks, just as in the case of the Euclidean plane. And if those landmarks uniquely tell me my position in the space or my identity in the space, I will say that R resolves that space. Now, why is this an interesting concept, at least to me, is because this function allows me to represent abstract objects as Euclidean vectors. And that could be useful in machine learning problems where this distance d is correlated with the problem I'm trying to learn to classify or I'm trying to learn to regress. So there is also something good about this representation, and it is that due to the triangular inequality, the L infinity norms of the representation of 2 points x and y in the original space cannot be larger than the metric d in the original space. And that is a good representation because it says that if 2 points are close in the original space, their embedding using this resolving set have similar coordinates, okay? And that's a good way to represent. It's kind of saying that if two people have a similar social security number, they have similar characteristics, which is not true, yes? But if you think this vector of distances acts as a social security number that also tells me, oh, these two people were born on the same town or have a similar income, etc., just because the representations are similar. So in that regard, it's a really good object to study. Now, as you can expect, studying the object comes with some challenges. And the most important thing you would like to do is to minimize the size of that set R because it defines the dimension for the representation. So the metric dimension of a space is by definition the size of the smallest resolving set of that space. And we are going to denote that with the letter beta, beta of xd. Now, in finite spaces, finding this is a difficult problem, NP-complete. And in practice, people find resolving sets using something called the information content heuristic, which unfortunately is very prohibitive on the size of the original metric space. However, it has a guarantee that the resolving set that the ICH information content heuristic gives you is comparable to the true metric dimension of that space up to a logarithmic factor in a relative scale. But on the spaces that I will be discussing, X grows exponentially. So by taking the cube root, you run out of luck very fast to find resolving sets. Okay, so the notion of metric dimension actually started in graph theory. In graph theory, you have a graph, you have your vertices, and the distance you use is the shortest path distance. And a lot has been done to understand the metric dimension of graphs. So for instance, if the graph is simple and connected, the only way it can have metric dimension 1, if it has n vertices, is that it's isomorphic to a path graph. And also if it has n vertices, the graph has to be complete if its metric dimension, and there is a typo here, is n minus 1. That's the only one that can happen. For a non-path tree, meaning not a segment tree, the metric dimension is the number of leaves minus something called exterior major vertices. And there is an algorithm not only to compute the metric dimension, but also to find resolving sets, which can always be taken as subset of the leaf space of the tree. More recently, the asymptotic metric dimension of Hamming graphs of dimension k over an alphabet of size A has been determined exactly. And with a student, we recently showed that if you replace the Hamming distance by the Levenstein distance or the edit distance over sequences of length from 0 to k, the metric dimension is of order AK squared. I don't think it's tight, but it's kind of close to be the correct metric dimension, at least asymptotically. Now, more recently, the concept of metric dimension has been studied at the level of random graphs, specifically the Erdos-Rengi, and Bolobas and collaborators determined 3 regimes for the asymptotic metric dimension, depending on some technical constraints on the average degree of Erdos-Rengi. And finally, at the level of metric spaces that are infinite, there hasn't been much done, but these are, I think, very notable results that if you have a metric space that is complete convex and every pair of different points resolve it, then it necessarily has to be isomorphic to the real line. And in subspaces of the Euclidean space, when you use the L2 norm, the metric dimension has to be 1 larger than the dimension of that space. It has also been studied for the unitary sphere under the geodesic distance and also for the hyperbolic space under the geodesic distance in that space. So that's kind of the general idea to show you all what has been done. I want to mention that the notion of metric dimension, even at the level of graph theory, is a very active area of research. Like I get on the archive 1 or 2 emails a week of a new paper on the notion of metric dimension. Yeah? Again? Sure. Is the size of the smallest resolving set, the least number of landmarks to determine your position in the space. All right, so there is a huge literature on the notion of a metric dimension. So with some collaborators, we wrote this review paper. You can point at the QR code, but there we not only talk about the metric dimension as the concept I'm introducing it, but also variations of the concept and applications of the concepts if you are interested in that. Okay, so but this is the topic that I really want to focus today, Jaccard metric spaces. So we are going to be working with a not empty and finite set X, and we are going to be looking at the power set of X. And when I have 2 subsets of X, A and B, I can define the Jaccard distance. Well, Jaccard defined the Jaccard distance as when the sets are different is the cardinality of their symmetric difference divided by the cardinality of the union. And you can show that this is a metric space in the sense that essentially satisfies the triangular inequality. So the questions I would like to address is, first, can we find non-trivial resolving sets of this Jaccard space? And when I say non-trivial, is because in a metric space, the whole space always resolves it, the whole space. So that's not fun because usually the whole space is tremendously large. Then what is the metric dimension of this space? And I don't know the answer, exact answer yet, but I know the asymptotic order. And can we find nearly optimal resolving sets, which is important for applications? Yes, when I represent data as subsets of a certain vocabulary, for instance. All right, so to fix some ideas, consider X to be 1, 2, 3, 4. Using the ICH algorithm that I told you a few slides ago, it determined that this is a resolving set. And you can verify in this small power set of X that that's the case, because if I construct the distance matrix between all of the power set and each of these three landmarks, you will see that none of these two vectors of distances are repeated in different rows. And that's the definition of resolving the space, yes? Meaning, for instance, the set 3, 4 is the only set at distance, Jaccard distance 1 from 1, 2, Jaccard distance 2/3 from 2, 3, and Jaccard distance 3/4 from 1 to 4. No other set is at those distance from those three landmarks. So because I need three sets or three landmarks suffice to resolve, the metric dimension is less or equal than 3. But in this small case, you can construct, look at exhaustively all sets or all resolving sets or pseudo resolving sets with two landmarks, and you will see that there is always a collision. So that being said, the metric dimension has to be exactly 3 in this case. But again, I cannot play that game a lot because the power set will grow exponentially fast. And the ICH is cubic on the size of the power set, yeah? Okay, so one of the first things we could do, this is my student Alex Paradise, was to show a sufficient condition that if a set R of landmarks resolves 2 to the X, it must separate different elements, meaning if I have 2 points in the space, then there is a landmark that contains 1 point but not the other. And it also either covers all of the space X, meaning the union of all the landmarks is X, or is almost X except for 1 point, okay? But these conditions are only necessary, but they are not sufficient, yes? But at least if you try to guess a resolving set, you can immediately rule out if one of these two properties fails. Now, when you are dealing with metric dimension, usually one of the bounds comes very easily. In this case, a lower bound comes very easily. So we can show that the metric dimension of this Jaccard space has to be at least of order size of X over the logarithm of the size. And I will tell you very briefly why. So the idea is if I have a resolving set, that means that this transformation has to be 1 to 1. But when I compute the distance between a set A and a set R, and I use inclusion exclusion, you can see that it's a function of the size of A, the size of R, and the size of the intersection of A and R. But that means that if I fix K and I have a fixed R, the only thing that matters for the Jaccard distance is the cardinality of their intersection. But because A has cardinality K, this cardinality has to live between 0 and K. So this ratio can take at most K plus 1 different values. And by Pigeon principle, the number of vectors on this side, which is at most k plus 1 to the number of landmarks, cannot exceed the number of subsets of x of size x. So that holds for every k. So you can choose a max in k, and the lower bound comes when k is half of the reference x set. And that gives you that. Now, you could say, well, why didn't you choose a different k? It's because the upper bound will match that lower bound in asymptotic order. Yeah. Okay, so now here was something surprising, at least to me, because the Jaccard distance, I mean, it's not a very simple distance like the Hamming distance, for instance. So what we realize is that if you pick up any point in X, that's going to be a fixed landmark. Then the set that is a singleton or the complement of the singleton or the empty set can differentiate, at least one of these landmarks can differentiate any pair of subsets of X of different cardinality. Yeah. So when you realize that, it seems, oh, well, this problem seems trivial. Yeah, well, it seems trivial, but that came as a blessing because we were having problems characterizing the metric dimension when A and B have the same cardinality. And then we realized that when A and B have different cardinalities, it's a very simple problem. Yes. So this proposition reduces the whole problem of characterizing the metric dimension to learn how to resolve all subsets of X, pairs of subsets of X of the equal size. That's the challenge that remains based on this little result. So how did we do that? Well, we simulated the metric dimension for different sizes of X. Here's the sequence that was given to us by the ICH algorithm. We look at the sets we were seeing here, and besides the necessary conditions, we couldn't tell any particular pattern, except that the average side of this of the landmarks were, this is not a good linear regression, but were roughly a half. Yes, so on average, the size of a landmark, remember landmarks are subsets, were half of the size of the whole space. So we said, okay, so we know something, can we exploit it? And in order to exploit that, you're like, well, I wanna find a set R that is small and for which this transformation is 1-to-1. So the most basic question is, when can a coordinate of a different A and a B be equal? So we can call those collisions or equidistant sets. So when two sets are at the same Jaccard distance from a common set R. And here's something that was the holy grail to open the problem for us, at least, and was to no longer think in terms of sets, think in terms of binary vectors, meaning represent sets as sequences of zeros and ones, which is the indicator if an element is or not in that set. And we realized that if we give 3 sets and we define this other vector, this quantity times the vector of A minus this quantity times the vector of B, then if there is a collision on A and B at equidistance, then R has to be orthogonal to that vector. And conversely, if R is not empty, but is orthogonal to that vector, we can guarantee that those two Jaccard's distance must be the same. And then using these two things, one can show that if A and B have the same size, then the Jaccard distances are equal if and only if R is orthogonal to the difference of these two vectors. And now this may seem like a change in notation to say that two fractions are equal, but it's actually more than that, because dealing with fractions is not nice when you don't know the numerator and the numerator exactly, but representing this collision as an inner product is nice because inner products are bilinear. So I can start to play now around with that difference A minus B. So the star here is because I only want to resolve pairs of the same size. Okay, that's the star. Okay, so now I want you to remember this. I told you I didn't see any pattern except that roughly that slope is 1/2. So we said, okay, well, let's suppose that I will choose landmarks that are binomial, the set x, 1/2, meaning that every point is in the landmark half of the time, and those events are independent overall. So the question to learn to resolve sets of the same size is, if I give you a set of landmarks, produce a random ID in that way, how can I guarantee that the probability that R union R0 does not resolve 2 to the x goes to 0 as the size of x tends to infinity? I know that resolves pairs that have different cardinalities, and I'm hoping that this will resolve pairs that have the same cardinality. Now, in principle, I would like this to be less than 1, but for practical reasons, if I'm given a large set x, I would like the probability of not resolving being very low, so this has practical use. So that's where the inner product idea came very handy. So here's the idea. What is the probability that this union does not resolve? Well, this resolves pairs of the same different size. So I need to focus what's the probability that the randomized part does not resolve, meaning there are always collisions. The social security numbers are the same between A and B, but A and B are different. Well, but I said earlier that this collision can be represented as an inner product when I think of A and B having a binary representation. But when you subtract these two binary representations, every element common to A and B is assigned the coordinate 0. So the only thing that matters are coordinates that are in A, one coordinates that are in A but not in B, or are not in A but are in B. Yeah, and the question is, well, what does this mean? Well, this is a vector. I would call it Z. And when one looks carefully at this vector, one realizes, well, it has 0 or plus or minus 1 coordinates. The sum of the coordinates is 0 because for every 1, there has to be a negative 1 because A and B have the same size. And there has to be at least 1, 1 and at least 1 negative 1. So the sum of the absolute values is 2. But then this inner product is doing this, is selecting some of the 1 coordinates in that vector and subtracting some of the 1 coordinates in this vector. And each coordinate is selected with probability 1/2. So the only way that that inner product can be 0 is if 2 binomials subtracted give the value 0. And the parameter in the binomial is the number of ones or the number of negative ones in this vector that I'm calling Z. And it's a trivial calculation to show the probability that 2 independent binomials are equal or their difference is 0 is this quantity over here. Okay, but that means that for each R, I know this probability, but I'm choosing the R independently. So now I can bound by sigma additivity. I assume that R has K landmarks. So I take that probability to the K, and this is the number of choices I have for the vector Z with I ones and I negative ones. And now comes a painful for me, a painful analysis of how to choose K small so that this tends to 0. And we were able to determine that as long as K is of order X over ln of X over 2, that does the job. This tends to 0. And therefore now I have found an upper bound for the metric dimension that is the same order as the lower bound I found earlier. So we know the metric dimension is X over ln of X. Yeah. Now, when you say like, okay, well, let's apply this to X Twitter posts. Well, if you apply it to X Twitter post, a typical American, I don't know Canadians, use between 20,000 and 35,000 words. So that's the size of X. thinks of a Twitter without grammar as a collection of words, yes, that's not gonna work always, but it's gonna be able to do some representation for some classification problems. And overall, social media posts are negligible compared to this. So the previous result, while interesting mathematically, is not very practical because I'm not interested in looking at any possible pair of arbitrarily large tweets because tweets cannot be arbitrarily large. So we ask the question, well, if I restrict the size of the subset of X, how many landmarks do I need to distinguish those sizes? And we realize that as long as we choose K at least of order the square root of X, this set that now uses the complements of the landmarks resolves all possible pairs up to size square root of X over ln of X, yes? And that gives us a practical problem to start trying to apply this on social media settings, yes, as a way to represent information. And that being said, thank you for your attention. I know I went super fast. The archive paper is posted there. And I want to acknowledge Alex, a Bachelor Accelerated Master student at CU Boulder that helped me with all the simulations, all the coding. And it's always fun when you work with a student. So thank you.